Here we're trying to maximize a certain function based on a constraint. To do that, we have to set our constraint equation equal to 0 to find our constraint function, and we can then plug the constraint function into the Lagrange formula. Now that we've done this, we can do a little simplification, and now take each partial derivative with respect to x, y, and lambda, set these equations equal to 0, and solve for x, y, and lambda. Most notably, we really need to solve for x and y. That's what we care about. Now, there are many algebraic ways to solve this. You've learned them in high school. You've seen some of them on previous videos. But I'd like to mention one thing that may or may not pique your interest in terms of researching. One thing you can do is take this equation and rewrite it with the x variable first, write it in a more traditional order. You can then take the bottom equation and bring the constant term to the other side. And there's one really cool technique for solving these things that is very easy to do and not labor intensive and not super algebraic. It does, however, require that you have a Texas Instruments 8384 and that you know how to do something called inverse matrices. What you could do is access the matrix features of the calculator by hitting the second key and then the matrix key, and simply calculate the inverse matrix times the constant matrix, where these numbers are stripped straight out of the problem. The purpose of this video is not to teach this method. If you have no idea what I'm talking about, this might not be a great path for you, and so if that's the case, then just use ordinary algebra and slog through all the messy work. I, however, would rather not do a bunch of messy work, and so I'll often use this method on my calculator. I don't have any videos produced exactly on how to do this, but YouTube is absolutely full of solving systems of equations by matrix inverses, so feel free to research that one if you like. Either which way, this matrix multiplication or just the regular algebra will lead to the answers for x, y, and lambda. Again, the purpose of this video was not to teach matrix inverses, but rather to either remind you of something you learned in a previous class or to spark interest so that you can do your own research. Either way, after having solved for x, y, and lambda, I can plug in my x, y values to the function and find the maximum of this function. Now, to confirm that it is a maximum, what I did is I took a nearby point that satisfied the constraint equation just to confirm that I would get something smaller than my original value. And you can see that negative 2469 is smaller than negative 2464. So the fact that a nearby point produced a smaller function value confirms that, well, it doesn't confirm, but it gives high degree of evidence that we probably have a local maximum there. So what I did, by the way, if you're wondering where these decimals came from, is I plugged 46.1, which, by the way, is just a random number near 46. I plugged 46.1 into the constraint equation. I solved for y. When I solved for y, I got 52.04, and that's how I knew the corresponding y value, and thereby have found a point nearby. And concluded, because I got a lower answer, that that point must be a maximum.